probably the fastest kind of 5-minute overview, or 6 or 7-minute overview, right? There is a video that's already there, or there are actually a few videos that are already there that will take you through this, okay? But I just want to point out a few things. So what we're going to do today is come up with an equation that you don't remember, that I don't remember very well, okay, all the time, that relates the radius of curvature to the local strain, okay? This one is, it's neat, it's important, it's good, we use it to derive other things, but the big one that we come up with today is something that you could be asked on an interview. I was, in fact, asked on an interview, okay, to calculate the bending stress across the beam. Fortunately, so when you become like old, this stuff is like so, you're like old and you haven't taught it, right? You're like, oh man, I have to like remember back like 4 years ago, like what in the world, okay? But anyway, but that one I was actually able to remember. So this formula will be something that you take with you, and these pictures give you an idea of how do we calculate the radius of curvature and related to the local strain, right? And you can kind of begin to see, oh, interesting, like this radius of curvature is the rho, right? And it's kind of interesting to think about how you have these kind of semicircular arcs that you're cutting out, or you're producing as you apply a moment, okay, to the beam. And then if you have a moment inside the beam, we actually get a set of stresses where above the middle of the beam they might be in compression or tension, and then below the middle of the beam they're the opposite. Okay, and you can you kind of see that here? Can you get an idea that, oh, the material here and here, they're getting closer to each other. So if I have a bend of radius like this, where the center of the radius of curvature is above the beam, that means that what is going on here? Is this tension or compression above?
Compression.
Right, and then look, if I go below, back down here, what's happening? That's the opposite, right? And so I don't know if you ever thought about that. Did you ever think about this? Like anytime you step on a piece of plywood and it sags, the top of it's in compression and the bottom of it's actually in tension. So we're going to formalize, as you watch the videos, okay, we'll formalize these relationships, okay? So you see, we get, and you can read, you can go into Hibbler's book if you like, all right? And this is kind of the relationship that comes out of this. So the local strain along the beam is equal to minus y over rho. So rho is the radius of curvature. What is this term y? Well, as you look into it, what you learn is that y is the distance above what's called the neutral axis. Okay, so over the longitudinal axis. Actually, I think CDL I think these terms end up being a little bit mixed. Hibbler refers to the neutral axis kind of as this axis that's, if you're like right here, it's like going in to the board, okay? But it's along what he calls the longitudinal axis, right? So I think of neutral axis, you can think of longitudinal axis. It's essentially this line or this curve that I can trace along almost the middle, we'll say, okay? And there's ways to calculate this. Actually, it's kind of like the centroid of the cross section, okay? Is where you have this line of zero strain. This is really cool if you're designing flexible electronics. Okay, so you're like, what? Yeah, so John Rogers and a bunch of people with whom he's worked, he was at big name in flexible electronics, they made a killing out of this idea. So like, guess what? If I put my wire along this neutral axis, I can have a flexible structure, but my wire doesn't stretch. And so now I can make flexible wires, I can make things I can bend, but I'm not gonna destroy my conductors. So it's a clever idea. And you can kind of now begin to predict. Okay, and why is it 0? So the way you can say it's 0, okay, is because it's at y equals 0. That's where the strain is going to be equal to 0. And if the strain is equal to 0, right, sigma equals E epsilon, this is actually a form of normal stress, right? So that's going to be 0 stress. 0 strain, 0 stress. At least due to bending. Okay, so then, and you can go through this, you get an opportunity to answer a question. And this question, okay, is going to use what we said about this negative y over rho with a strain and the Poisson effect. Like, oh man, what's up with that? Well, look, and I try to exaggerate here. If the top is in compression, right, that actually means that the top portion is going to get a little wider. Why? Because I'm bringing it closer. Just imagine that I've got like a bunch of beams, or not a bunch of beams, it is a beam, a bunch of bars, right? I've got a bunch of bars, and so that top bar is experiencing the most compression, top bar being up here, right? And this bottom bar is experiencing the most tension. So it actually gets narrower at the bottom, and it gets wider at the top. Okay, and you can calculate that because you can figure out what the longitudinal strain is, and then we know that Poisson ratio is the ratio between the longitudinal strain and the latitudinal strain. Okay? So that's one part. Okay. Next, we're going to talk about bending stresses, and this is a famous formula. Bottom right, the flexure formula. Okay, this is the one that you want to have down on your formula sheet, and you want to have in your head if it's going to be a technical interview. Why? Because this is pretty straightforward and people know it. And it shapes this idea that now you saw it like in the that slide of the truck moving across, I don't know, the those other things. That thing was bending moment. Right? And you saw that there was like a spike in the middle for the bending moment. Or it's like whatever. Yeah, that means that that's where the stress is going to be the highest. Okay? So now this is like earth-shattering. All this time we've been doing bending moment and shear force diagrams, and finally you now know, or we know, what the stress is based on the bending moment. And so you can make the prediction of whether or not your beam is going to fail. Okay. Question 2 will essentially say, hey, come up with the bending moment diagram here and just plug it into the flexure formula. Remember I said J is pi over 2 c to the 4. Okay, remember that for the polar moment of area? Well, this one, if it's cylindrical, if it's a circular cross section, then I is actually equal to pi over 4 c to the 4. Okay, I comes before J. So I is pi over 4, c to the 4, J is pi over 2, c to the 4. It comes out from, it's a very similar equation. Okay. The famous, you should also remember this, if it's a rectangular cross section, you have this equation right here, BH cubed over 12. So if now I know the width of the cross section and the height, then I can calculate what I is. And if I know that, and I know the moment, and I know bending stress is 0 when y is equal to 0. That's when you're on a neutral axis. But when is it maximum? It's maximum at the top or the bottom surface. Okay? That's usually half the thickness. So now I've got bending moment, which, you know, for many intents and purposes is P times L. And I've got a thickness in the numerator, right? That my or minus my. I've got a thickness in the numerator. I've got a thickness cubed in the denominator. So the bending stress goes with 1 over h squared. Does that ring a bell? Do you remember this? Remember we talked about the scaling, right? Of how much load a beam can support? 1 over h squared is that relationship. We said it was 1 over thickness squared, 1 over the width just to the first power, and then 1 over, or with L. Actually, I guess I got it flipped. All right. If I make it twice as thick, then it's going to be 4 times as strong. If I make it twice as wide, it's going to be twice as strong. If I make it half the length, it's going to be twice as strong. Okay. Okay, so rapid. Okay. All right, second moment of area. You'll learn when you watch the video about how we calculate these out. You'll learn an incorrect way to do it, a correct way to do it. Okay, and this problem is intense. Okay, I guess I've got one of the, and so you can look at 2015 exam 2, or you can come to this document that we talked about, all right, on the website. Did it disappear? Okay, last time for some reason it disappeared when I went over here. You go to session, well actually it doesn't really matter which session you go to, but if you go to session 13, which is where we are, you'll see all this stuff, and you can come into the fall 2023 notes, and if we drop down to session 13, okay, you'll see some tips on how to attack this problem. Okay. So that's pretty much all we've got time for. That's really rapid, okay? But the takeaways are like what we said at the beginning. We now have an ability to figure out what the stress above and the stress below this kind of invisible plane might be. We have the ability to think about what the strain below and the strain above are for this beam. Okay? And we can think about how bending moments that we've been calculating for a while are related to stress and strain. It's really cool. Okay. So you have, I think, about 6 problems to do over the weekend. With the helpers, it shouldn't be too bad. And they're going to be due at 1. I will not be here. I'll be in Massachusetts for a meeting and for work. I'm not at the beach. Okay. I wish I were. If any of you surf, let me know. We'll have to jam. So the videos that I think are already there should be sufficient. But I'll